Dear student friends, in our previous presentation, we have seen the basic aspects of the high voltage power transmission, could it be AC or DC, and how exactly our HVDC transmission can be conceived, right? So now in this particular presentation, we shall try to see what are the basic, constituents of both HV AC as well as HVDC transmission system, both HVAC as well as HVDC transmission system. Later, we shall confine our discussion only to the HVDC transmission system. Okay. Now, when I speak about that, basically I am trying to tell you about the EHV, AC, and DC links, right, between the two ends of the system, right? How exactly you are going to create the links, whether it is extra high voltage AC or HVDC. Right now, let us start from the EHV AC system first, whatever we have seen here, the EHV AC system. So, in the EHV AC system, if you try to see the basic configuration, right? So, that is called as the single circuit three-phase AC line. Okay, so now the single line diagram of that has been represented here. You can see here you have got the AC systems on either side of the link here, right? Followed by a circuit breaker here, then the transformer, then the three-phase line represented by a single line here. Then you have got the series capacitor here, and if you now sectionalize this, right, this is going to be symmetric on either side like this. Again, you will have a transmission side, the transformer on the receiving end, followed by the circuit breaker, which is AC, then the AC system. So this is how the entire thing, as far as the single circuit three-phase AC line looks like, right? And of course, as it is mentioned here, it requires the transformers at both the ends, and as long as the transformers are the integral part of the link, then only the circuit breakers are required, right? And again, needless to mention that the capacitor here provides the series compensation, because most of the times the lines are overloaded, right? Whenever the lines are overloaded, it is necessary to provide the capacitive compensation, right, in order to maintain the power system parameters as per the desired values. So therefore, the capacitor is provided as the series compensator. So this is the basic or the primitive model, which is the single circuit three-phase AC line, which is definitely suffering from several drawbacks. So what are those drawbacks and how exactly we will overcome those drawbacks? We shall now look in our next slide. You can see here. So basically this diagram represents a similar diagram what we have taken earlier, but here we have got two parallel lines, right? And as you can see here, these two parallel lines are required for the reliable transmission of power, right? Very similar to the previous diagram only, but only thing is that you have got two parallel lines which are connected by means of this particular link here. So now the long AC links are sectionalized by means of the intermediate switching stations, right? So these are the intermediate switching stations. So that is how the long AC transmission lines are sectionalized, right? So this particular part represents the aspects of the sectionalization, right? And basically this sectionalization is required for the purpose of limiting the over voltage during the charging of the transmission line. Second very important thing is to have the futuristic plan to add the generation as well as the load, right? In the earlier system, right, it is very difficult to have the additional generation or load to be connected to a single circuit system, whereas here it is definitely possible for us to have the addition of the generation as well as the load as a futuristic requirement. And the third point here is, you can see here you talk this about the grounding transformer, right? So generally the grounding transformers are, the auxiliary transformers which are required to provide the ground connection as long as your transmission system or the transmission lines are delta connected, right? So for that purpose also, it is possible for us to have the provision to connect the grounding transformer. So now compared to the previous system which we have seen in our earlier slide, right? So this system, the one which I have shown with the parallelized line, right? So this has got higher degree of reliability as well as the operational advantages compared to the single line circuit, right? So now these are the basic two types of the EHV-AC links, right? But we will confine our discussion to the HVDC links. Now this particular diagram which is being represented here, right? It represents one typical HVDC link. Again, the line diagram here. You have got an AC system because we have seen that earlier on either side of your transmission system. The basic operating scheme is AC in nature. Then you have got the circuit breaker here. Then you have got the shunt capacitance followed by a rectifier. A rectifier comes into picture where this converts your AC into DC, right? Then you have got a smoothing reactor here. Then you have got the DC line. You can see here you have represented the DC line with a couple of conductors here, right? So then very similar to what we have seen in our earlier slides. So this is going to be symmetric about this particular point. Again, you have got the smoothing reactor, and here you have got the inverter wherein the DC is again going to be converted back into AC, followed by the transformer here, then the shunt capacitor, the circuit breaker, and the AC system on the other side, right? So now if you look at this, particular diagram, this particular part, what we see here, right? This represents a typical HVDC link, right? And on either side of this, you have the conventional AC components, right? So this is called a single circuit DC link, right? Could it be two lines or single line? I will tell you what is the meaning of two line or single line depending upon the different links that are used in the HVDC system. And the second thing is that the rectifier or inverter are always meant for the reversible operation. That means this rectifier can act as either a rectifier or inverter. This also can act as either a rectifier or inverter depending upon whether you want to have the power flow in this direction or in this particular direction. So now those directions will decide the mode of operation of these devices, which we typically refer to them as the converters, right? The converter could be a rectifier or an inverter, right? Then the circuit breaker, right? So circuit breakers will be on the AC side here, right? You can see these circuit breakers, the conventional circuit breakers, and you have got the shunt capacitances as well, right? Shunt capacitances here, basically you have to see that the shunt capacitance are at the AC side itself, right? Basically the shunt capacitance are used to improve the power factor, as you know, also to have the better stability of the system or to maintain the stability of the system, right? Then you have got the smoothing reactor, right? Whenever you speak about the smoothing reactor, they are with respect to the DC system. The smoothing reactors, whatever we are looking here, they are with respect to the DC system. So they are basically to limit the transient voltages, the transient DC voltages, right? So the reactors are basically limit the di by dt, okay, the rate of change of current. So they are basically to suppress the transient DC voltages to a lower value, right? So this is the general structure of a typical single circuit DC link. This is a very important point to be noted. It is a single circuit DC link, and again very similar to how we have seen the single circuit EHV AC link, right? So the single circuit DC links are also having certain limitations, right? So now what are those limitations? We will be able to see only when we study about its successor, right? So now you can see this system. So this system is very similar to what the parallel EHV AC link we had seen with respect to a single circuit EHV AC link, right? So now if you look at this line again, these one and one, right? One on either side. So basically these isolators, they are to connect one of the parallel links with the other, and you can see here the sectionalization is done with the help of 2 and 3, right? So now you have got a lot of flexibility here in case of there is some fault in the system, or one particular part of the system is required to be shut down for the maintenance or something like that. You can definitely understand how it is possible for us to have the diversion of the power here, right? So now 3 to 4 conductors provide high reliability. Basically, this complete structure is meant for having the higher reliability, right? So the bus tie switch 1 is normally kept open. So as long as the tie switch 1 is kept open here, you have two independent systems operating in parallel compared to what we have taken a single system in the previous slide, right? So now during the fault in the second line, the switch 3, during the fault in the second line, the switch 3 is opened to isolate it, and if at all the opening of the switch 3, right, is for a short period of time, definitely you need not connect one. But if you connect one, then it is possible for us to restore the power, or you have the restoration of the power from one parallel line to the another parallel line. So this is how you can have a higher degree of reliability and flexibility in the operation if you consider a 3 to 4 conductor lines of the HVDC link, right? So in this way we have got these four systems. Okay, one is the first, whatever we have seen is the conventional or typical single circuit EHVAC line. We have seen what are its limitations. Then we have come to the parallel EHVAC line. Those are the two types, and a very similar counterparts even exist in the DC lines, right? A single circuit DC line as well as the circuit with 3 to 4 conductors, which are meant for providing the higher reliability, right? So now with this particular background, let us now try to see what are the different types of the links or the DC links which are used in your HVDC system, right? Now, when I speak about the DC link, there are basically three types. As you can see, the first type here, that is called as the monopolar link, right? The first type is referred to as the monopolar link, right? So now mono, it means one. Polar, there will be only one polarity, right? So now if you look at the first diagram, of course both the diagrams are almost overlapping, but anyway you can just refer to this diagram. So this diagram refers to a structure of a monopolar DC link, and as you can see here in the monopolar DC link, it has got a single conductor, generally of the negative polarity, and it uses the earth or sea for the return path of the conductor. What I mean by earth or sea, if you have a DC link which are intercontinental one, so if it passes across the sea, then the sea bed will be acting as the return path for the current. Otherwise, the ground itself is acting as a return path, right? So now here basically there are so many disadvantages here, right? Since it uses the earth as the return path, so you always it is not there is no guarantee that you get the proper working of these things. That all depends upon the external condition. So but it is the simplest one. You can see here it uses one conductor with a negative polarity with the ground or sea return. So all the structure and other things appear to be very simple here, but the drawback is that since it makes use of the earth as the return path, there are the issues related to the overall reliability of the system, right? So now that takes us to the next type, that is the bipolar link, right? So compared to the monopolar link, what is bipolar link? You should be able to understand in the diagram which we have drawn here. So this is the diagram which represents the bipolar DC link. So in the bipolar DC link, it has got two conductors, as you can see. One is positive and another is the negative, which is to the earth. Okay, the link has a converter station at each end. You can see here this link has got the converter station here as well as here, and the second link has got converter station here as well as here, right? And the midpoint of the converter station, right, the midpoint of these converter stations are earthed. So this is very important point to be noted through the electrodes, corresponding electrodes, right? And the voltage of these earthed electrodes, whatever we are having here, is just half the voltage of the conductor used for the transmission of the HVDC power here, right? So now whatever the voltage having here, it is just half of the voltage of the conductors used to transmit the HVDC, right? Now the very important advantage of this bipolar link is that if any one of the links, right, fails to properly operate, right, the link gets converted into a monopolar link. So this is a very important advantage, right? Whenever there is a problem with the link, one of the links goes faulty, right? So it acts as a monopolar link, right? And now the half of the system continues to supply the power because it is acting as a monopolar link, right? So these type of bipolar links are very common and popular in our HVDC power transmission system. Generally, the bipolar links are very popular if you look at the overall scenario as far as the DC links are concerned in our HVDC transmission. Okay. Now, the rated voltage is always expressed as plus or minus X volts, because now it could be either plus or minus with respect to what we are at this particular point, right? So that's why this is a very important point to be noted. Rated voltage in a bipolar link is always taken to be plus or minus X volts, right? So this is about the monopolar and bipolar, but you have one more which is called as homopolar, right? So homo means similar, right? Polar means the polarity. Homopolar links, right? So now if you look at the diagram here, if you look at the diagram whatever we have drawn here, this represents the diagram of a homopolar HVDC link, and it has got two having the same polarity, usually negative. The homopolar having the two or more conductors with the negative polarity, and it always operates with the earth or metallic return, right? So it always operates with the earth or metallic return, right? And these poles, whatever we are speaking about, poles here, this is one pole and this is another pole. These poles are operated in parallel, right, which reduces the insulation cost. So this is a basic reason why the homopolar systems were deployed, in order to reduce the insulation cost. But in comparison with the bipolar links, the homopolar links always are inferior in their performance. So that is the reason why nowadays the homopolar links are not generally used. Whichever the links that are very popular are the bipolar links, right? So therefore, if you summarize these things, right, you have got the monopolar link, one conductor with a negative polarity with a ground return or C return, but the questions are the reliability of the power transmitted here because of the ground connection. In the bipolar, there will be two terminals, one positive and one negative. You will be able to make the differentiation between the three also later, right? And here, this is the most popularly used type of HVDC link, and its rating is generally given in plus or minus X volts, right? Unlike the bipolar link, in the home link, you will be having two or more conductors having the same polarity, right? Unlike the bipolar link, and it always ground return, but the basic idea was to reduce the insulation cost and all, but nowadays these things are not that popularly used. Okay, so now these are the basic introduction about the constitution of EHV, AC and DC links, then followed by the three different types of the DC links which are used in your HVDC system. That is the monopolar, then bipolar, as well as the homopolar links. The other aspects of this HVDC systems, how it is being compared with HVAC systems and all, I will come back with my next presentation.